Thank you very much. Thank you also for organizing this night conference and giving me the opportunity to speak. So what I will speak about is at the border between asymptotic combinatorics, probability, statistical mechanics, but the main object that I want to put forward to your attention is really a combinatorial object and a conjecture about its enumeration. So I think it can be of interest here. Maybe we can do it. So I am sorry, but I have to make a small introduction, a scratch course on Tracy-Widom distribution, because I think that part of the audience is not aware about what it is. It's just a probability distribution, a cumulative probability distribution. If you look at this one, sorry, and you take the derivative, and this is ordinarily the probability distribution. I have just compared in orange the Tracy-Widom distribution, and in blue the normal distribution. They are almost the same, but there are some difference. The difference is that in the cube. So here the two in one case you have a parabola x squared. When you take the logarithm, there's a case we have x to the cube or x to the 3/2. And this is related also to some scaling exponents in statistical mechanics, which can be in one case 1/2 and in the other 1/3. So in physics, it's very important. And this is just a graph, but there is a formula. It arose originally in the context of random matrix models, but it has an explicit expression. Explicit may be a strong word, but you can write it as a determinant of some operator, Fredholm determinant of some integral operator, which is trace class, and has some kernel acting on function on a interval, and the kernel is a recurrent. Okay? And so this Tracy-Widom distribution was discovered or invented in 1994, and then it has been observed in a plethora of models, many models, you see. And so, especially mathematicians start to think about some universality of this distribution, just like the normal distribution is universal because you have the central limit theorem. Here, you expect to find it in some situation with some universality, but if you think a little bit, you realize that most of these models are in projection with random matrix model or non-intersecting lattice path or tilings, and they are all determinantal models. That is, all correlation function, all statistics can be expressed in terms of determinant of some kernel. Okay? So there are some exceptions. With the red dots, I put two exceptions, which are AZEP and transport electric chain, which actually was discovered here in the physics department here in Ljubljana. And so a natural question is, can we observe Tracy-Widom in general in non-free fermionic, in non-determinantal models? So this was the main motivation of this work. And ASM is a non-determinantal, that's why it's so difficult, and that's why a lot of people study it. And so this is a kind of introduction, okay? So I will not define once more alternating sign matrices. Everybody knows here what it is. I will just denote by AN as usual plain enumeration, and by AN, R, the refined enumeration in the standard way. And I will introduce some generating function for the refined enumeration, where you use normalized numbers. And due to Zellberger result, you can plug in the number, this number, and you see that the generating function is some hypergeometric polynomials. So let me define the frozen corner enumeration, which is a different refinement with respect to the usual one. We consider the enumeration of ASMs under the requirement that we have a corner of 0, a square of zeros in one corner. You can choose any corner. This is, of course, not really important. And so you choose an S by S square. And if you choose, for instance, the top left square, then the definition is that the scientist must be 0 for all ij smaller than s. I give you an example here, and I give you the enumeration of 7 by 7 ASMs and the enumeration of 7 by 7 ASM with a 3 by 3 frozen corner. Okay, so we want, for reasons that I will explain later on, we want to enumerate such something. But first, let me mention a few properties of this BNS. I will denote this frozen corner enumeration by BNS. So, of course, it does not depend on the corner. You can choose any of the four corners for this square, frozen square. And if you think a little bit, BNS is a decreasing function of S. It is a strictly decreasing function for S smaller than integral part of n over 2. And then it's just a constant 0. I will show you why in a minute. And also, if S is equal 1, you are asking for having a 0 in the top left corner. So you are asking for the sole 1 in the first row to be anywhere but the first position. And so you have this nice relation. And we have other relation, and I will explain him. To explain them in a more intuitive way, I will go to osculating lattice path or six-vertex model, or as I have learned that I have done for 20 years, bumpless pipe dreams. So it's never too late to learn. And well, you have seen this picture many times. The point is that the first, the list of weights over there, the first row is implementing the alternating condition of alternating sign matrix, while the boundary condition, the second row, is implementing the sub-rule on to be 1 on all rows and columns. So frozen corner enumeration is in this language translated to the condition that you have a fully packed path in a square in the top left corner. And you see, let us suppose that S is larger than integral part of n over 2. You see that the top left square is frozen. You can do nothing with it. You have only one configuration. And for instance, in the top right rectangle, you have 4 lines entering from the top, but 5 going away from the left. So you cannot satisfy ASM's conditions. So you have 0 ASM satisfying. You are not able to satisfy ASM requirements as soon as S is larger than n over 2. And this gives you these conditions that I have mentioned above. Another condition is that another property appears if you consider n even and S exactly equal to n over 2. Then what you see is that you have exactly 5 lines, in this case, S lines in general, entering from the top and going to the left. So you have in your top right corner an ASM. You have another ASM here down in the bottom left corner. And so the total enumeration will be just the square of ASM enumeration of size S equal n over 2. Okay. Let me show one more example because it's instructive, I think. You consider now that a situation where n is equal to 2s plus 1. So you have a frozen square of size S, and then you have a rectangle of size S times S plus 1 here on the top right. And you have 5 paths entering from the top, 4 exiting from the left. So you must have some paths exiting from the bottom. And so if you think a little bit, you will see that this rectangle is essentially describing refined, if the path exit at position J is this totally, then this means that you have an ASM refined at position J. The same for the other one. For the bottom right corner, you have an ASM refined at position K. Okay? And so here what you have only one path which must go one lattice path, and so you have to count all possible configuration of directed lattice paths on a rectangle of size J minus 1 times K minus 1. And so you obtain this result. You see that you have to sum over all possible position of J and K, and so you see that the frozen square enumeration is related to usual refined enumeration by this simple relation. Of course, you can go on. You can consider the case where you have 2 lines exiting from the bottom, 2 lines in the bottom right corner, but then they start to interact according to the C-vertex rules. They are not anymore non-intersecting lattice path. When you have 1, it is, but when you have 2, it is not. And so calculation becomes more complicated, as for instance, Ilse know very well. So how many ASM with a frozen corner? This is what we want to ask. To count them, to enumerate them with our computer, we will use the bijection with monotone triangles, which has again been mentioned several times. I use a description where the triangle has its longest side horizontal on the bottom. And there is this nice bijection. And indeed, this is the most efficient way to enumerate ASMs, but because for some reason, this algorithm is more efficient. So in the case of a frozen corner, it is easy to see that you have just to restrict your enumeration of monotone triangle with the condition that on the first S rows of your triangle, the number cannot go, instead of going from 1 to n, has to go from 1 to n minus s. That is to satisfy this condition. Okay? So we took just the code there is a code in the Bressu book, 4 lines of Mathematica to enumerate triangles. You just modify it in this way, and you can count monotone triangle with a frozen piece. This is the result. And what to say? For instance, concentrate on this B12-3. B12-3, you will factorize it. You see it does not factorize at all into small primes. So, well, it's not a surprise. You know, enumeration is related to a lot of multiple sums, and you don't know what to do with this. Now I come back a little bit to what is the main motivation to study this frozen corner enumeration, because numbers are not round, so it's not maybe so interesting. Well, it is interesting. Again, due to asymptotic combinatorics. As you know, ASM develop limit shapes as n becomes large. Here I use this code of colors. So this is a 100 by 100 ASM. But if you increase the simulation, and at the same time you rescale the mesh of your lattice of your entries in an ASM in such a way that the size of your domain remains of order 1, what you see is that the limit shape becomes more and more sharper and sharper. You know, you see that the distinction between frozen and disordered region, between zeros and non-zeros entries, becomes sharper and sharper. So well, you could say just, but to study this, we can consider ASM refined to the position of finding, say, some -1 at some position I and j. But this is too difficult. I mean, I don't think anybody in the room is able to compute this quantity. It would be fantastic. You can do this, for instance, for domino tiles, but not for ASM. So we look for a simpler refinement. It appears that a simpler refinement is just a frozen square enumeration, because it is simple enough to be computed explicitly, but at the same time, it is not a boundary correlation function. It enters into the bulk of your matrix, so it can test the limit shape. Actually, in principle, you could choose a rectangle, but for the rectangle, we have some formula, but we have no combinatorial formula. So actually, we have a closed formula for BNS. We have been having it for a very long time. It's 18 years old now. It is a constant term formula of this kind. As you see, the structure is very similar to the expression, for instance, evaluated by Ilse. Again, everything is expressed in terms of this G, which is a generating function for refined enumerations. And what to say? We computed it using quantum investigating method, integrability, going further with respect to what was explained by Filippo in previous talk. And this formula is a rigorous one, and you can check it with number. We were able to check it until n equal 12. Not further, because the integral formula is very difficult to evaluate. The problem with this formula is that it is not very suitable for asymptotics. Just like monotone triangle, we have already a formula for frozen corner enumeration, monotone triangles, but how to do asymptotic with it, nobody knows. And here it's the same. We can do some very rough asymptotic, which will help you to find the limit shape, but here we want to address a more sophisticated problem. So to do asymptotics, it is a known fact that a very useful kind of representation is in terms of freedom determinant. When you have freedom determinant, you can do asymptotic. There are a plethora of methods available to do this asymptotics. So we looked for some freedom determinant representation. The first step is to find an S by S determinant representation, which is of freedom form, that is of the form determinant of 1 minus something or plus something. So we worked a bit about this, and we were able to find some expression for S equal 1 and 2 and 3 and 4. And indeed, the expression is as follows. You introduce some function f, which is again essentially a combination related to the generating function of refined enumeration. And then you build some matrix Mij, which is of size S. And then you build this determinant, and it is now I see the problem. So yes. So this actually is a proposition. It's rigorously proven, but only for 1, 2, 3, and 4. Or we did it, well, you know, when you have determinant of 1 minus something, you can expand in terms of traces and combination of trace and power of trace. When you have your integral, you have 2 poles essentially, so you can expand it according to the number of residue you compute with respect to one pole or the other pole. Then you make some identification, and for S equal 1, 2, 3, 4, this identification allowed us to build this matrix. And now our bold conjecture is that this holds for any S and any N. What we, sorry, the proposition, okay. It's for S equal 1, 4, but for any N, I would like to. Okay, so we have this formula, and it would be nice to prove it for several reasons. So first of all, this formula is, you see, we computed, using monotone triangles, we computed everything till n equal 20. And of course, our conjecture, otherwise I would not be here, reproduce all these numbers. So I think this is a very strong test. And why this conjecture is useful? Because when you have some limit shapes, then you want to find the fluctuations. You consider n large but not infinite, and then you want to see what are the fluctuations of the frozen boundary around the limit shape that you have calculated. So what is a frozen boundary? So we define for each ASM, you know, I focus on, here you will have, in this path description, we have some external paths. You choose some point, some entries ij, and then you say, if all this rectangle is made of zeros, then this entry ij is in the frozen region. So this defines the frozen region as some external region here. And we focus on this top left quadrant. So we don't mind about what happens here. We have some separation between frozen and disordered region. And there is a uniquely defined boundary, which is called the frozen boundary. So the question is, what is the distribution of this frozen boundary for large n as you distribution according to what? To random sampling with uniform measure of ASMs. So first question is, what happens when n goes to infinity? Does this distribution concentrate on some arctic curve, on some limit shape? And the answer is yes. This was conjectured a long time ago by now, but then it has been recently proved rigorously by Agarwal in the ASM case only. So you rescale the entries of your matrix in terms of coordinates y, which goes downward, and x, which goes horizontally. And you have some equation. This is actually an ellipse, but you have to consider only the part of ellipse, which is in the top left quadrant. This was shown by Philippe in previous talk. Okay. So we have this red curve, which is the Arctic curve, which is the result. But the next question is fluctuations. So here again, I have a picture in terms of path, but it's again ISMs. And instead of studying the fluctuation of the whole path, external paths, because this would be a bit difficult for us, let us concentrate on the fluctuation of the intersection of the most external paths with the diagonal. So this is a point. You have many samples of your ASM, so you have a discrete random variable which lives on this diagonal. Okay? And so as we know from the explicit form of the Arctic curve, we know that for large n, this random variable concentrates at some value. The value is what I call here YC. It is just the value you obtain when you can compute the intersection between the Arctic curve and the diagonal. So this we already know. Now we want to compute the fluctuations. So to consider the cumulative distribution of the fluctuations, that is the probability that your fluctuating point on the diagonal is larger than some S, is exactly given by this frozen boundary enumeration, modulo some normalization. This PNS of psi, the probability of having psi larger than S will be, of course, around 1 when S is very small, when S is in this close to the corner, and it will drop to 0 as soon as you enter the disordered region. But what we are interested in is the way it behaves. Of course, in the infinite limit, it will be just a stepwise behavior. But now we are interested in the fluctuation that is in the profile. Okay? Is this profile Tracy Widom or normal distribution or what? So experience analogy with dimer models, because you know dimer models, in particular, the homeotics of Hatzek diamond is essentially two enumeration of ASM, and in that case, the fluctuations are governed by Tracy Widom, as was shown by Johansson long ago. And also there is a result by Ayer, Chita, and Johansson, which says that TCCP obey another Tracy Widom, but this is a strong hint that ASM would obey this GUE Tracy Widom distribution. However, there is no rigorous derivation of this for ASM at the moment, but we have anyway a rigorous result about some other one, about this determinant of 1 minus m. If we evaluate the determinant of 1 minus m for large S, it is an S by S matrix, but we can rewrite it as a Fredholm determinant. We evaluate for large S and we tune S to be just very close to the limit shape, to the boundary between order and disorder. What we obtain is indeed by analytic calculation, Tracy Widom distribution. The problem is that this determinant of 1 minus m is only conjecturally related to this probability. Okay? So because that of 1 minus n is equal to BNS over AN, only conjectures. Okay. So I hope I have explained to you why BNS is interesting. Essentially for reasons related to asymptotic combinatorics. We have provided a closed form expression for BNS. It is very strongly supported by numerics, I would say. And also, if you prove this conjecture, you prove at the same time Tracy Widom distribution for a non-determinantal process, which is by itself quite a nice result. And also, this result, which is at the moment still conjecture, is anyway in full agreement with other kind of numerics for this Tracy Widom distribution and with the conjecture made by Ayer, Chita, Johansson on the basis of TSS. Okay. So now, okay. So I think that this BNS deserves a proof. Thank you very much.